Hello everyone, I'm Wenqing from Institute of Computing Technology, Chinese Academic Sciences. Now I'm working at ByteDance. I'll introduce our work, CETOFS, a high-performance file system with host-server collaboration for remote storage. I'll introduce from the following aspects. First, the background and motivation. NVMe over Fabrics is a block storage protocol that enables access to remote SSDs over networks such as TCP, RDMA. NVMe-OF exposes remote SSDs as local block devices, and users can build local file system on them. In the work, we focus on high-performance SSD, for example, Optane SSD and RDMA network. The kernel file system can directly access remote SSD. We show the workflow of a write operation. Applications write issues the write syscall on file. The write request traverses the file system stack, including the virtual file system and block layer. The request is then forwarded to the initiator side NVMe driver, where it is packed as an NVMe-OF command and sent to the target via RDMA send by the NVMe-over-RDMA driver. Upon receiving the command, the target side NVMe-over-RDMA driver extracts the NVMe-OF command and fetches the data from the initiator via RDMA read. The target then generates the IO request and writes the data to SSD through the NVMe driver and block layer. Once the SSD data writing is complete, the target sends a completion response to the initiator via RDMA send. Finally, the application's write is notified about the finish of data writing. Building a file system based on a kernel mode NVMe-OF with RDMA driver incur heavy software overhead. To show it, we measure access latencies of 4 KB random read on raw device and file system ext4. For local file system, the soft stack, including syscall file system and NVMe driver, occupied about half of the total latency. However, for remote SSDs, software overhead accounts for a higher proportion, which hurts performance badly. To further quantify the overhead of main components in the software stack, we break down the software stack latency for file system based on remote SSD. We measure the latencies spent on syscall file stack NVMe over RDMA driver and NVMe driver for write operations. We see that the NVMe over RDMA driver becomes a major overhead, occupying about 36% of total latency. The root cause is that handling RDMA interrupts in kernel brings high latency when accessing the remote storage. Existing kernel file system exhibit poor scalability when accessing remote storage. We measure aggregate write throughput across concurrent arrays based on ext4 and FTOS, where each thread concurrently updates a shared 10 GB file. Local and remote represent accessing locally attached SSD and remote SSD. We have two observations. First, accessing remote storage decreases the throughput by 63% due to the network overhead. Second, they show poor multi-core scalability, especially for remote SSDs, decreasing by 30%. The execution process of a write operation can be split into three seamless phases. First, the initiator sends requests to the target, and the target fetches the associated data from. Second, the target writes data into the SSD. Third, the target sends a completion response back to the initiator. The first and the third phases incur networking latency, and the second phase incurs SSD write latency. To protect concurrent accessing of a shared file, the end level lock is employed to serialize the execution of concurrent reads and writes. So they are executed sequentially, which not only hurts the file system scalability, but also utilize the hardware resources. Field atomic I/O is an important feature of file system. However, it means expensive data movement on remote storage. We take the journaling mechanism as an example. The journaling mechanism first write logs into the log area on the remote SSD. Then the checkpoint process reads logs from the remote SSD to the initiator and writes them back to the target area on remote SSD. Furthermore, updating journaling-related metadata requires extra IOs across network. Thus, the journaling mechanism incurs more than twice data movement across network, which hurts performance. Next, I will introduce the design of this work. To address above challenges, we propose CETOFS. We show a high-level overview of CETOFS design, which mainly contains the following components. First, the kernel file system. It handles metadata operations. Second, user space library. It handles data operations entirely in user space, using pool file request queue to submit IO requests. Third, target request handler. It is responsible for handling IO requests, performing permission checking and concurrency control. First, why is permission checking is required? That's because we place the data operations in user space for high performance, which takes specific challenges for permission checking. Since application threads use the user space driver to issue IO commands, application can send requests with any device address to remote storage, which may corrupt the file system. For example, modifying the file system metadata. To handle this problem, we offload the permission check into the target. Its key idea is letting T-handler check whether the block address of an IO request is legal. To achieve this, we design a block granularity reverse permission table as a target. We divide the blocks of the file system into 3 types: free blocks, blocks for storing metadata, and blocks for storing file data. We define an owner for each block and use the owner ID to identify it. We set the owner of any free block and any metadata block to be KFS, and its owner ID is 0. The owner of one data block is its corresponding file. Its owner ID is set to be the file ID number. Also, CETOFS assigns a request queue to each file. Each opened file has a request queue, and the queue's owner is the file. Each queue is attached with an access permission flag, read only, or rewrite for the application that accesses the file. For example, application 1 opens 2 files A and B, which maintains 2 request queues for communicating with handler. T-handler performs the permission checking according to the following 2 rules. First, the requested operation type should match with the permission flag of the submitting request queue. Second, the owner of a requested block should match with the owner of the submitting request queues. This rule can prevent application threads from accessing illegal addresses. We take the read operation as an example to show how CETOFS performs permission checking. As shown in this figure, when an application thread issues period operation to file A, ULab first translates the file offset into the device address. Then it sends the IO request to the target server. ULab subsequently pulls request queues for detecting request completion. The worker thread in T-handler receives the request and extracts the request block address. Then it checks the permission flag of the request queue and the owner of the requested block. If matched, the worker thread issues an NVMe command to the underlying SSD and then posts for completion. Otherwise, this IO request is reported to incur illegal permission error. To reduce the network wait time, we propose concurrency control offloading technique. Its key idea is allowing the initiator to send IO requests in parallel, even conflicted requests exist. Meanwhile, letting the target perform request serialization to guarantee correct concurrency. As for the traditional kernel file system, additional networking latency exhibits serialization overhead. In CETOFS, it sends IO requests in parallel, and the target performs request serialization to guarantee correct concurrency. It can reduce the network waiting time significantly. To achieve this, we design a request group to control the ordering of IO requests as a target. A request group consists of adjacent IO requests accessing the same file but without having conflict with each other. We create request groups as the initiator. The figure shows an example of request group creation. There are six threads, T1 and 2 T6, that issue read or write requests concurrently. They are trying to acquire the spin lock, and the order of the acquiring lock is R1, R2, W1, R3, R4, and W2. Thus, there are 4 request groups totally. After creating groups, these requests can be submitted to the target concurrently, which greatly saves their waiting time. To guarantee a correct concurrency, thandler handles this request in order. Thandler processes request group by group, which restricts concurrent accesses to the disjoint portions of the file from different groups, thereby limiting concurrency. To address this limitation, we propose a merging group policy as the initiator, which allows adjacent groups without accessing flags to be merged with low overhead. As shown in this figure, all requests except W3 are merged into the same group G1 as they have no range conflicts. As a result, they can not only be submitted in parallel, but also be executed in parallel as a target. This greatly improves concurrency and the hardware utilization. To minimize data movement overhead, CETOFS offloads the field atomic I/O support to the target. It provides atomic APIs to enforce atomicity. Thandler maintains metadata for transaction management and performs checkpoint operations in the background. CETOFS also adopts transaction-aware submission and completion, which use a delayed submission strategy to batch MMIO and doorbell writes. Next, let me talk about evaluation. We use two servers with 2 Intel CPUs, Connect X5 RDMA NIC, and 1 Optane SSD. We compare CETOFS with X4, FTFS, and UFS. We use the FIO and fixed mark workloads. First, can CETOFS reduce the kernel software overhead? In single-threaded read-write tests, CETOFS eliminates kernel software overhead, reducing latency by up to 50%. Second, can CETOFS scale with increasing threads? We use the fixed mark DWM workload, where concurrent threads have high contention for writing the same shared file. CETOFS offloads concurrency control to the target, reducing network waiting overhead. Moreover, CETOFS merges the request groups without conflicts to allow concurrent accessing to disjoint portions of a file, which improves its scalability significantly. Last part is concurrent. We propose CETOFS, a high-performance file system with host server collaboration for remote SSD. It designs a collaborative architecture to place data planned entirely in user space, meanwhile separated permission checking from in-kernel control plane. It exploits the processing capability of a remote server to offload 3 tasks: permission checking, concurrency control, and failure atomic I/O guarantee. The offloading mechanism greatly reduces the networking overhead. Currently, I'm working on the BitDance elastic file system, a high-performance distributed file storage service designed to deliver elastic scaling for both capacity and performance. It supports multi-applications, especially for AI workloads. If you are interested in learning about EFS, please feel free to contact us. Thank you for listening. That's all. I'm glad to answer questions.